So I want you to imagine something for a second. Imagine you are walking along and you find this massive, towering steel skyscraper. But it's not on a concrete foundation. It's perfectly balanced on the flimsy roof of this tiny, rotting wooden cabin.
Right, which makes absolutely no sense.
Exactly. It shouldn't stand. I mean, the foundation should just crack immediately. The physics completely fail. The math simply does not work. But you're looking right at it, and there it is.
And you just have to deal with the fact that it's there.
Yeah, and that is exactly the situation the James Webb Space Telescope has just dumped onto the desks of astronomers worldwide. Welcome to today's deep dive, everyone. We are exploring a stack of notes today about a discovery that is so baffling, so entirely counterintuitive that it's defying the very laws of physics we've relied on for decades.
It really is. I mean, the stakes here cannot be overstated. We are looking at a finding that forces us to question the fundamental blueprints of reality.
It feels less like a natural universe and more like a literal glitch in the Matrix.
It does, because when an instrument as powerful as the James Webb Space Telescope sends back data showing a system that mathematically should not exist,
Right.
it isn't just some minor anomaly. It's not a rounding error in a spreadsheet. It means the textbooks detailing how the universe operates, specifically how stars and planets form, they might need to be completely rewritten from page one.
Okay, so to fully appreciate the sheer scale of this plot twist,
Yeah.
we really need to understand the bedrock rules, right? The rule book that we thought governed everything.
Yeah, we have to start at the beginning. What happens when a star is born?
So break that down for us. What is the standard model here?
Okay, so the standard model of planetary formation is based on this very strict logical progression. It all starts in a stellar nursery.
Which is just a massive cloud of gas, right?
Exactly, a giant cloud of molecular gas and cosmic dust just hanging out in space. And eventually, a pocket of this cloud becomes dense enough that it collapses under its own gravity.
And it starts pulling everything inward.
Right. And as it collapses, it spins. Most of that material falls into the center to ignite and, become the star itself. But because of the conservation of angular momentum, the leftover material doesn't just fall straight in.
It kind of spreads out.
Yeah, it flattens out into the swirling ring of debris around the newborn star.
Okay, I always picture this like spinning a ball of pizza dough in the air.
That's a great way to look at it, actually.
Right, like you spin it until it flattens out into a disk.
Yeah.
So the star is that dense center of the dough, and the flattened part is the leftover gas and dust.
Exactly. And that swirling debris is what we call a protoplanetary disk. So over millions of years, the slow, patient work of gravity takes over in that disk.
Slow and patient being the key words there.
Very slow. Initially, you just have microscopic dust grains bumping into each other. They stick together through simple electrostatic forces.
Like dust bunnies gathering under your bed.
Exactly, like dust bunnies. Just static cling, basically. But once those clumps get large enough, gravity finally takes the wheel.
So pebbles become boulders, boulders crash together.
Right, they become planetesimals, and eventually they sweep up their entire orbital paths. They just keep clumping together to form planets.
Okay, so this is the established rule book. And the ironclad rule that came with the standard model is that the size of the planets you can build is, like, strictly dictated by the size of the star that formed in the center.
Yes. The universe enforces a very strict accounting system for these ingredients. You can't just conjure matter out of nowhere.
Right.
A star's mass determines its gravitational pull. So smaller stars, like red dwarfs, they have significantly less gravitational pull when they form.
Meaning they pull in way less material from that initial molecular cloud.
Exactly. Which leaves behind an incredibly thin, sparse protoplanetary disk. And less material in the disk simply means fewer building blocks for planets.
I want to visualize the math on this with a baking analogy, if that's okay.
Oh, go for it.
So if you are baking, right, and you only have this tiny little bowl of leftover batter, which in this case is our small star's sparse disk of gas and dust, you can only bake a small cupcake.
Right, a small, dense, rocky planet.
Like Earth or Mars.
Yeah.
It is physically impossible to take that tiny bowl of leftover batter and somehow bake a giant 3-tier wedding cake.
Which would be a massive gas giant like Jupiter.
Exactly. The ingredients just are not in the inventory. You can't make a wedding cake out of a tablespoon of batter.
So for decades, have we just been operating on the assumption that small stars are basically trapped in this cupcake tier of planetary neighbors?
Absolutely. The accounting system just doesn't allow for anything else. The cupcake tier, as you call it, is dictated by the mass ratio.
So it was just accepted as mathematical fact.
Yes, astronomers could look at the mass of any low-mass star, calculate the absolute maximum possible mass of its surrounding dust and gas disk, and confidently state the upper limit of planetary size in that system.
Because building a gas giant is fundamentally different from building a rocky planet, right? Completely different. To build a gas giant, you need a massive amount of solid material to form a core very quickly.
Like, how massive are we talking?
About 10 times the mass of Earth. And you need to build that core before the star's solar winds blow all the loose hydrogen and helium gas away into deep space.
Oh, wow, so it's literally a race against time.
Exactly. The planet has to build its solid core fast enough to start, vacuuming up the surrounding gas before the star essentially turns on the fan.
And blows all the building materials away.
Right. And a tiny star simply does not have enough solid material in its disk to build that 10 Earth mass core fast enough. By the time a rocky core is even partially formed around a red dwarf, the volatile gases have already dissipated.
They're just gone.
Gone. The math simply did not allow for a gas giant to form around a low-mass red dwarf. It was considered an unbreakable physical limit of the universe as we knew it.
Which brings us back to the glitch in the Matrix.
Right. The discovery that breaks all of this.
So the James Webb Space Telescope stares deep into our galaxy at this tiny low-mass red dwarf star. And right next to it, in a close orbit, it finds a gas giant the exact size of Jupiter.
Yeah.
And the scientific community officially named this the Forbidden Planet, which is such a cool name, by the way.
It is, but it's called that because the mass discrepancy is just jarring. I mean, red dwarfs are typically only about 10 to 20% the mass of our sun.
Wow, that's small.
Yeah, very small. So finding a Jupiter-mass planet orbiting one is gravitationally absurd. The inventory of the star's original disk is entirely in the red.
Hang on, let's look at the actual physics of that wooden cabin supporting the skyscraper analogy.
Okay.
If the star is incredibly small and low mass, and this planet is disproportionately massive, how did this massive planet not just crush the tiny star, or, I don't know, fling them both out of orbit? How do they even coexist gravitationally?
See, that is exactly where physicists are truly losing sleep, the mechanics of their orbit. Because when we think of an orbit, we usually picture like a bowling ball sitting perfectly still in the center of a trampoline.
Right, and a marble rolling around the edge.
Exactly. We think the sun stays still and the Earth moves, but gravity goes both ways.
The planet pulls on the star just as much as the star pulls on the planet.
Yes.
Wait, really? So the star isn't sitting still at all?
Not at all. It's actually being yanked around in circles by the gravity of its own planet.
That's crazy to think about.
It is. They orbit a shared point of gravity called a barycenter.
A barycenter, okay.
Right, so in our solar system, the sun is so unbelievably massive that the barycenter is mostly inside the sun itself.
So the sun just looks like it's vibrating slightly.
Exactly. It has a tiny wobble. But when you have a tiny low-mass star paired with a disproportionately massive gas giant,
That center of mass shifts.
it shifts dramatically outward. So the wobble induced on that tiny red dwarf by this Jupiter-sized behemoth is incredibly violent. The star is being aggressively whipped around in a tight circle by the gravity of its own planet.
So they're locked in this intense gravitational tug-of-war.
A very chaotic tug-of-war, yes.
And the tiny star is just punching way above its weight class just to hold on to this thing.
Exactly.
But if we go back to the birth of this system, how does a star with such weak gravity manage to hold on to enough gas to form that giant in the first place? I mean, you said it was a race against time, right? And the gas went to expand and blow away?
Yeah, it's like trying to pack a snowball in the middle of a windstorm.
That sounds impossible.
It mathematically should be. The tiny star doesn't have the gravitational muscle to hold the gas together tightly enough before those stellar winds blow it all away into the void. To build a Jupiter, you need a massive gravitational anchor.
And the red dwarf just doesn't provide it.
It doesn't. The math definitively says the gas should have scattered millions of years before a skyscraper could ever be built on that cabin.
The ingredients weren't there, the gravitational muscle wasn't there, the time frame doesn't work.
Nothing about it works.
Yet the telescope sees it. We are staring right at it.
We have the data. It's real.
So we are stuck trying to figure out how this skyscraper got on top of the cabin. Which brings us to the only two explanations scientists have been able to put forward to make sense of this.
And both of them are pretty radical.
Right. Both of them require us to completely rethink fundamental reality. So let's start with theory number one. Our fundamental understanding of gravity and planetary birth is completely wrong. Basically, it's an inside job.
Right, so Theory 1 demands that the massive planet actually did form right there in the sparse disk around that tiny star.
But we just said that's impossible.
Under our current rules, it is. If this inside job occurred, it means everything we just established about the standard model, the physics of accretion disks, the race against time, the mathematical certainty of how mass clumps together, is just fundamentally flawed.
So we are missing a massive piece of the puzzle regarding how matter accumulates.
A huge piece. It would mean there is a mechanism of gravity that we are entirely blind to.
Like what? Could the protoplanetary disks of red dwarfs just be significantly more massive than we currently calculate?
Well, that is one possibility people are looking at, but the issue is it creates a cascade of new problems.
Of course it does.
Because if a disk around a tiny star is actually heavy enough to build a Jupiter, that disk would be wildly gravitationally unstable.
Because it's too heavy for the star to control.
Exactly. It would likely just collapse in on itself, or it would be torn apart by its own competing gravitational forces long before a planet could even form.
So to make Theory 1 work, matter would have to coalesce much faster, or somehow much more efficiently, than our current laws of physics even allow.
Yeah, it forces us to question if we even understand how gravity operates on a galactic scale when planets are being born. We would basically have to tear up the textbook on accretion.
Wow.
We might have to consider alternative models, like disk instability.
What's that?
It's a theory where instead of building a planet slowly from dust to pebbles to boulders, a massive chunk of the gas disk suddenly just collapses all at once into a giant planet.
Like instantly.
Well, very rapidly in cosmic terms. But again, the math says a red dwarf's disk shouldn't have the density to trigger that kind of sudden collapse in the first place.
So we're back to square one. We'd have to rethink everything from how solar systems organize themselves to the basic equations of mass and gravity.
Yeah.
That is terrifying for anyone who relies on those textbooks for their career.
Absolutely. It's a massive headache for physicists.
But then we have theory number 2.
The rogue planet theory.
Right. Theory 2 proposes that the giant planet didn't form there at all. It wasn't an inside job. Instead, it was captured from deep interstellar space. A cosmic kidnapping, basically.
And honestly, the rogue planet hypothesis is just as mind-bending as the first theory.
Because rogue planets are just planets floating around without a star, right?
Right. The universe is incredibly violent, especially in the early days of a stellar system. When multiple gas giants are forming and migrating, they can play this chaotic game of gravitational billiards.
Gravitational billiards. That sounds destructive.
It is. Planets get too close to each other, their massive gravitational fields interact, and one planet can literally be violently slingshotted completely out of its solar system.
It just hits escape velocity and gets ejected.
Exactly.
Doomed to wander the freezing void of deep space without a star. Just a rogue Jupiter drifting through the darkness.
Yeah. And we know these rogue planets exist, right? We have actually detected them drifting out there in the interstellar medium.
That is so eerie to think about.
So theory 2 suggests that one of these wandering behemoths just happened to drift past the specific tiny red dwarf and became ensnared in its gravitational pull.
Okay, hang on. If it's a rogue planet, doesn't that require a ridiculous, almost impossible amount of luck?
Oh, extreme luck.
Because I'm picturing it like trying to catch a speeding cannonball with a baseball mitt. A rogue Jupiter would be flying through space at, what, tens of thousands of miles an hour?
Sicily, yes.
It has tremendous momentum. How does a tiny star have the gravitational brakes to stop a massive rogue planet and gently guide it into a stable orbit?
The short answer is it shouldn't. The physics of orbital capture are incredibly punishing.
Like, how precise does it have to be?
Well, for a tiny red dwarf to catch a massive rogue planet, the rogue would have to approach at the absolute perfect angle and the absolute perfect speed.
And if it doesn't?
If it approaches too fast, its momentum just carries it right past the star. It slingshots around the gravity well and flies back out into deep space. It might alter its trajectory, but it never enters orbit.
Okay, and if it's too slow?
If it approaches too slow or, hits the wrong angle, gravity pulls it all the way down and the planet just crashes straight into the star.
Destroying them both.
Completely.
So there has to be some way to bleed off that speed, right?
Yeah.
Some kind of cosmic friction to slow the cannonball down just enough so it settles into a stable orbit without crashing?
Normally, yes. Orbital capture usually requires a third body.
A third body.
Right.
Like another planet.
Or a moon. Say the rogue planet had a massive moon, the gravitational interaction with the star could strip the moon away and transfer the rogue's kinetic energy to the moon, basically flinging the moon into space.
Oh, so losing the moon acts as a brake.
Exactly, that energy loss allows the rogue planet to slow down enough to be captured.
Okay, that makes sense.
Or, alternatively, if the star still had a thick, massive disk of gas, the rogue planet plowing through that gas could drag enough friction to slow it down.
Oh, wait. We already established that a tiny red dwarf never has a thick, massive gas disk.
Bingo.
The inventory is too low. The ingredients just aren't there.
Exactly. The contradictions just keep piling up. The precision required for a tiny star to capture a massive rogue planet and bleed off its kinetic energy without a dense gas disk or an unobserved third body, and then somehow settle it into a stable, enduring orbit. I mean, it borders on the miraculous.
It's just statistically impossible.
We have never observed a process that could reliably explain how this happens smoothly. The braking mechanism is just entirely missing from the picture.
So if we look at the two options here, neither of them fits neatly into the reality we've constructed.
Not at all.
If it's an inside job, we totally misunderstand the fundamental blueprints of gravity and planetary birth.
Right.
But if it's a cosmic kidnapping, we have to accept that weak stars can effortlessly execute an impossibly complex gravitational catch without any observable braking mechanism.
Yes. Both scenarios break the universe in wildly different ways. I mean, the first means our foundational models of physics and gravity are just missing a massive variable.
We're just wrong about how gravity works.
Yeah. And the second means the galaxy is filled with chaotic, statistically miraculous events happening in the dark, just constantly rearranging solar systems in ways we never thought possible.
So either we don't know how to build a planet, or we don't know how planets navigate the void.
Pretty much. Which is a terrifying realization for astronomy either way.
It really is.
Yeah.
Because when you look at everything we've unpacked today, the failing math of the accretion disks, the impossible capture physics, the violent wobble of the barycenter, it leaves you with a deeply uncomfortable realization.
What's that?
The ultimate takeaway from the Forbidden Planet isn't just a quirky astronomy fact. It proves, without a shadow of a doubt, that the universe absolutely does not care about human textbooks.
Oh, not even a little bit.
We engineer these pristine mathematical models to feel secure, right? To feel like we understand things. But reality refuses to be boxed in.
It's so true. We build neat, tidy frameworks to comfort ourselves, to feel like we have mastered the dark. We map the stars, and we assume the rules we observe in our own solar system just apply everywhere perfectly.
But they don't.
No. Every single time we build a more advanced instrument, every time we use something with the unprecedented resolving power of the James Webb Space Telescope to look deeper into the cosmic void, reality just shatters our assumptions.
It forces you to wonder about the sheer scale of the unknown that is still out there. I mean, our sources pose a brilliant, chilling question. Are there millions of forbidden planets hiding in the dark?
Oh, almost certainly.
Are there millions of tiny wooden cabins out there with massive skyscrapers balancing on top of them, just waiting to be found? We've only looked at a tiny fraction of the galaxy.
Right, and statistically speaking, if we found a system this anomalous this quickly after turning on the Webb telescope, there are undoubtedly countless more.
It's just wild to think about.
Each one of them serves as a stark reminder of how young our science really is. Our models are just approximations.
They aren't the final answer.
No. Knowledge is most valuable when we recognize its strict limits. A discovery like this forces the entire scientific community to strip away their arrogance and stay deeply humble in the face of the cosmos.
I completely agree. And I want to leave you, listening right now, with a final, lingering thought to mull over, something to explore on your own that builds on what we've discovered today.
Okay, let's hear it.
We just spent this entire deep dive establishing that the strict, ironclad rules for where giant gas planets can exist are completely wrong.
Completely wrong, yeah.
The limits of the standard model failed us. The textbooks were incredibly short-sighted.
Yeah.
So, what if our strict textbook rules for where habitable Earth-like planets can exist are also completely backward?
Oh, wow. I mean, the implications for the search for extraterrestrial life there are massive.
Right. Because we currently only look for life in what we call Goldilocks zones.
Exactly, these very specific orbital distances where liquid water can exist. But that's entirely based on our current math and the assumption that life requires a system identical to ours.
Exactly. Could we be looking in all the wrong places for life just because we are trusting the wrong textbooks?
It's very possible.
If a tiny, weak red dwarf can secretly host a massive Jupiter through mechanisms we don't even understand yet, who is to say what other impossible worlds are out there?
We really have no idea.
What kind of thriving, habitable planets might exist in places we were mathematically certain they couldn't be? The glitch in the matrix might just be the new normal. Keep your eyes on the stars.